All right. Yeah. I hope my screen is visible.
Yes.
Thank you. So first of all, I'd like to apologize to all of you. See, last week I could not take a session because I was traveling and all of a sudden the internet was not working for me. So I had to postpone it. Okay. So I will hold a remedial session on this Saturday. Okay. So I guess the information has already been passed on to you. But anyway, I'm just announcing it here. I'll be holding a remedial session on this Saturday. That is 5th, right? 5th of March, I guess. So, sorry, 2nd of March, not 5th, 2nd of March, this Saturday. So, I hope to see you join the session. Okay. Today, I will be covering week 4. Okay, that the week that was supposed to be covered last week, in the last session, which I couldn't hold. Today, I will be covering the contents that were taught in week 4. Okay. So I know a lot of people, the assignments have already been done and they have been discussed also. But still, if you have any doubt, you can ask me now. I'll just try to summarize the points here and then moving on to the problems that I wanted to discuss last week only. Fine. So the people who have joined today, do you have any doubt from week 4? Any particular thing that you have in mind that you wanted me to discuss? If there is nothing, I'll just do it myself. The way I wanted to do it. Okay, all right. So in that case, I'll just follow my own style in that case. Well, so uh, okay. Anyway, so before that, this course is analog circuits. It's a MOOC NPTEL course, and this the instructor for this course is Dr. Jayanta Mukherjee. He's a professor in electrical engineering at IIT Bombay. Myself, I hold these problem solving sessions. My name is Mayank Anupam, and I am a PhD student in electrical engineering at IIT Kanpur. So let's start. Yeah. So hmm. First, in the week 4, what did we cover? So we looked at the feed effect of feedback and stability, right? So effects of feedback, some of those you had already seen in week 3, but a few more effects were shown in week 4, right? Like what is the effect on input resistance, output resistance, and all, right? How can you make a good this thing operational amplifier or maybe a transconductors amplifier and all? You learnt all those things. So if do you have any doubt in those things? Okay, I hope not. Fine. So then you moved on to the idea of stability, right? This was the most important thing that we discussed, that sir discussed in this week 4, right? Stability. In a negative feedback system, we often have the chances of the system becoming unstable. Did you understand the idea behind this instability thing? You see, if you have an open loop system, if there is no feedback in a system, the system is never going to become unstable. There is no idea of instability in that case, at least in the physical system that we know of. They can become unstable, but that's a whole different thing. Uh, we do not go into that, but in general, an open loop system will not become unstable. But it's only when you put feedback in the system there are chances that the system becomes unstable. So do you have an idea or a intuition why that should happen? Anyone? I know the instructor gave in detail the mechanism of stability and how to check whether the system is stable or not. But I just wanted to know whether you understand why should the system become unstable in the first place. In the negative feedback system, which is so good at controlling things, so why should the system become unstable in negative feedback system? All right, so let's see that. I just wanted to give this intuition to you. You see, let's assume that okay, first let's call this as, pardon my voice, I have got cold, so that affects my voice. Yeah. So let's say, Shu, that you are driving a car. Okay. Let's say you are driving a car. Now, uh, on the road, the signboards are kept which say that you have to limit your speed to, let's say, 60 kmph. Okay. On the road, you have these signs, right? Those of you who drive and must know that this has to be adhered to. So you have to drive at the maximum speed of 60 kilometer per hour. But at the same time, you also are getting late to reach somewhere, maybe in a exam or so. So you have to go as fast as you can, right? So the maximum speed that you can go at is 60 kmph. So definitely you want to stick to that speed, right? You don't want to go any lower. You don't want to go at 57 kmph. You want to go at as high speed as possible because you want to reach as soon as possible. Now, now, how do you do that? Let's say you are riding on the road and suddenly your speed becomes lower. How do you see? How do you see that your speed has gone down? I mean, let's say if you try to plot your speed versus time, okay. So this is the situation, right? This is the speed that you want to achieve. Okay. So this is, let's say, 60 kmph, and now let's say you want to achieve this speed. So let's say you have started here. Okay, you have started at some very low speed. Generally it starts with 0, so I'm not taking into, not going that back in time. So all right, now let's say you have started with this speed, and now you're trying to, you go up like this. You are accelerating, right? Here you are, what you are doing, you are accelerating, right? You're accelerating here. Okay, you're accelerating here. Then what do? When you reach this point, 60 kmph, or you will slightly overshoot, right? You will slightly overshoot, isn't it? Or maybe you don't overshoot. When you start reaching 60 kmph, initially you start with very high acceleration, right? You put your pedal on the, you press your accelerating pedal very tightly, and then you go like this initially, right? And once you start, Once you start coming to this speed, close to this speed 60 kmph, you start to reduce your acceleration, right? Right? You start to reduce your acceleration such that eventually your speed becomes equal to 60 kmph, isn't it? That's how you do it when you are driving a car, correct?
Yes.
Yes. So, guys, please talk to me, okay? When I'm talking, it feels like I'm talking to myself. No one is hearing. So, in the meantime, you also you also keep giving me your feedback. Fine. So, this is accelerating situation. Now, this is fine. This is a very good driver. You are going very. You have learned to drive, okay? But let's say there is a newbie in the picture, and he also has to go at very high speed. I mean, he also has to achieve the 60 kmph speed, but since he's a newbie, he's rash driving. His driving style is rash. Okay, so how will he do? He'll start with even higher acceleration. Okay, he'll start with very high acceleration, and once he's not stopping at he's not as he's going close. He's not reducing his acceleration. What he's doing, he puts a stop on the acceleration once he overshoots. Okay, once he overshoots this speed limit. So once he overshoots the speed limit, what he does, he removes his his foot from the accelerating pedal, and then he starts reducing the acceleration. But once he reduces the acceleration, again he reduces too much, and then he realizes, oh, I have gone down. So again he presses, but now he's slightly careful than earlier. So he's not going that high, he's not overshooting that high, but still he's overshooting, and eventually he also kind of settles at the 60 kmph speed, right? Do you understand that? Good. I
Yes.
hope you understand. So those of you who joined later, I'm explaining how negative feedback works in actual I mean real life, and the idea behind negative feedback. So this is basically negative feedback, isn't it? What you're doing, you're trying to achieve a certain speed limit, and you are controlling your actions to achieve that speed, right? Your eyes speedometer is the sensor, right, in this case, and it gives a feedback to you, your brain, right? And your brain instructs your hand, or sorry, leg, your foot, to take some action, correct? And that action is negative feedback. If your speed is higher, go lower, right? That is negative feedback. Your actions are trying to negate the effect of, I mean, negate the effect of feedback, right? I mean, something like that. Your feedback is such that your actions are opposite to that, opposite to the output. Fine. So this is also fine. Now let's say there is another person who does not know driving. Okay, who does not know driving. So which color should I use? I should use. Let's use red color maybe. Yes. In that case, this cannot be red. Let's use this color. Fine. So let's say a person is not doesn't know how to drive. How will he proceed? He has to achieve the 60 kmph speed, okay, which is our desired speed. But he what he does? He starts accelerating somewhere in the middle. He doesn't know how to drive. He keeps accelerating, right? Or maybe say he knows to drive, but his speedometer is broken. Okay, his speedometer maybe is broken. What speedometer shows is always equal to 30 kmph. Okay, let's say that the third person, which is this guy, his speedometer reading is stuck at 30 kmph. Okay, so what will he do? He'll start accelerating at a certain speed. He will start accelerating, but he will keep accelerating, right? Even when he reaches 60 kmph, he will not stop, right? Because according to him, the speedometer is what? It is speed is actually always 30 kmph, isn't it? So you'll keep going higher, 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 higher. So you see that the system in this case, you can never achieve 60 kmph speed, right?
Yes.
So in this case, what the system is? System has become unbounded, or the system is unstable in this case. Do you understand this? I mean, overall, your system, which is controlling the negative feed, controlling your actions to achieve the desired speed, has become unstable because you are not able to achieve a stable this speed, right? So this system is unstable. Now let's take a fourth case where the speedometer reading is not stuck, but it is very slow. Okay, speedometer responds very slowly. I mean, what is the, this is the third case, right? Let's take another case, fourth case, where speedometer is responding very slowly. Fine. So let's say again in this case I'll use a different color again, which is this one. Is this visible? I hope this is visible. Okay. All right. So this, in this case, let's say the speedometer reading is very slow. Speedometer response is very slow. So it will again start at a certain speed like this. I mean, let's say this guy is accelerating even faster or maybe slower. Okay, it starts accelerating slowly like this. Okay, but once it reaches 60 kmph here at this point, somewhere around this point, since the speedometer is very slow, it may be showing that the speed is still 40 kmph only. The speed is only 40 kmph, so it will again go. It will overshoot, right? It should overshoot. Is it overshoot, right?
Yes.
Yes. Now, once it reaches very high speed, which is let's say 90 kmph or so, at that time the speedometer said that the speed is 60 kmph. Okay, and then it tried to put a stopper again, and the speed is reducing, but the speedometer is again very slow. So it is showing. Sorry. At a time the speedometer reading has come to 60 kmph, right, and then it will start to stop. But what happens in that case, the speedometer is still slow behind, right? So it will still start increasing from this point, so it will keep reducing here in this case. Once it reaches 60 kmph again after reducing, right, the speedometer, since it is responding very slow, it may be showing a speed of 80 kmph or so, right? So when it reaches here also, what it will think? It will think that the speed is still higher, so it will again go down like this, right? And this time, let's say that the light has gone very low, and still the speedometer says that the speed is not 60 kmph. Once it is going certain once it has gone sufficiently lower, so that the speed is again showing at 60 kilometer per hour, it will again start accelerating, right? Something like this. And it may happen that in at this time the it may go even higher, right, than the last time, and this keeps going on. So in this case also you see that the speed is, in this case also you see that the oscillations in the speed are increasing with time, right? This is in contrast to this case, right, where the oscillations died with time. Do you get my idea? You get the idea basically here?
Yes.
Yes. So what is this system? This system, what is this? What is this system? What kind of behavior is this showing?
So which one? The dying one or the increasing one?
The increasing one, this gray curve, this one.
So,
What kind of behavior this is showing?
so definitely it's unstable.
Yes, good. So it is unstable. This oscillations here are not stopping with time. They are increasing with time, isn't it? And negative feedback here is failing. Correct? Right. Whereas in this case, in the case where oscillations died with time, their negative feedback system is actually working, right? So
Right.
this is kind of a analogy to uh, how the system actually works in the electronic world. Okay, there is a negative feedback and there is a sensor. Okay, similar to this case where we had a speedometer, there we have something else with senses, and then information based on that sense, based on what the sensor is sensing, information is given back to the input. Okay, it is fed back to the input, and the information that is fed back is then subtracted from the input. That hence the name negative feedback. Okay, fine. So now, can you from all of these discussion that we had till now, can you say something about the possibility of instability in open loop system which doesn't have any feedback? I mean, you're not trying to control anything. In that case, assume that you're not controlling anything, just that certain signal is coming and it is just going out. Okay, let's say this is an open loop amplifier with a gain A. Okay, so you have an input here, you have an output here. What is the situation? Can this system become unstable?
No, sir, because output will remain constant.
I mean, yeah, I mean, unstable, the whole idea of instability is we talk about bounded input, bounded output instability. Okay. So if this input is within certain bounds, the output should be within certain bounds, should not go to like infinity. Okay.
Okay.
So that is always going to be the case here, right? If the
Yes.
gain A is bounded also, right? It is not infinity. So that will always be the case here. So the whole issue of instability comes in negative feedback because here we have a feedback. I mean, certain thing has to be controlled, okay, and that control happens because the output is sensed and then fed back, and that whole thing, that sensing thing and then feeding back, it is not instantaneous. It requires some time, right? There is some time involved in that. The from the input to output, the signal goes from input to output, okay, and then again that output signal is sensed and fed back to the input. So that whole loop, it takes certain time to operate, isn't it? It is not instantaneous. Just at the case, just as that case we saw here, that the speedometer responding slowly, it is not instantaneous, it is slow, right? And if the speedometer is very slow, then you can have this possibility, isn't it? You can have the possibility that the system becomes unstable. You get the idea? So if the feedback is very slow, if the feedback is taking very long to operate, in that case, your system can become unstable. Do you understand?
Yes, sir.
Yes, very good. So if that you understand, I think this was the only thing that I want to discuss, stability. Another thing was about, one second. All right. So other thing was about, yeah, stability and pole location. Did you get the whole point which instructor was trying to make, correlating stability with the pole location?
Sir,
Yeah.
sir, you would you explain the terms marginally stable, unconditionally stable?
Oh, all right. So you see that, like in this case, okay, I'll come to that. Before, let me comment a little bit on the stability and pole location. So just now I explained that stability is very much dependent upon how much time, right? How much time it takes for the loop to respond, right, to the input, isn't it?
Yes.
So if the loop is very slow, if the feedback is very slow, there is a possibility of instability in the loop, right? In the negative feedback. So the whole idea of correlating stability with poles is based on the idea that based on this idea which I just explained. Let me say how. Let me talk about how it works. So one second. Hmm. So this is Hmm. Now, you remember that a few sessions ago I talked about an RC circuit, right? So in this RC circuit, we know that there is one pole, right? There is one pole in this circuit, isn't it? And the pole location is what? Omega is equal to, right? This is the pole location. Omega is equal to 1 over RC. Now, we know that there is, if you apply a unit step to this system here like this, what is the output response going to be? So, if we have a unit step, in this case, if we have a unit step like this, how is the system going to respond to this unit step? What is the output V out? If this is V in, what is the output V out?
Output will rise slowly and it will
Yeah,
fall also
so
slowly.
like this, and then it will try to do this, right? Isn't it?
Yes.
Fine, good. So in this case, I also explained that it looks like that the system is delaying, right? That due to this pole, the overall response is delayed, right? Something like that, right? I mean, ideally the output would have, if there was no capacitor here, if there was no pole here, ideally the output would have simply jumped, right? Like this. But now it doesn't do that. What does it do? It rises slowly. So it behaves like a delay, right? I mean, it achieves the, it becomes equal to Vi only at this point, right? Only after so long. So you can say that this is kind of like a delay, right? You can say something like this, isn't it? It behaves like a delay. The pole here, it behaves like a delay. It basically uh, adds a delay to the system, isn't it? A pole. I hope this idea is clear. Fine. So now coming back to the original point, if you have a system, negative feedback system, so negative feedback system is, there's an amplifier like this, right? And then you have this output here, which is fed back with a beta factor. This is beta, just beta. Let's say this is minus, this is minus, this is plus. All right. Now you have a system like this. Ideally, what do you want? The moment this V out, I mean, the moment you put an input here, immediately that input should be amplified like this, right? At the V out, and then a part of it should be fed back. A part of it should be fed back like this. All this should happen instantaneously, isn't it? You do not want any delay here, correct? But now let's say, because of the, let's say there is a pole in this A, right? This amplifier, it is not simple A, it is, let's say, A by S plus P, or maybe A by S plus omega P, okay? Something of this kind. So what does this pole do? We just saw, right, that a pole, it manifests itself as a delay in the system, right? So whatever information you put at this point here, at the input of the amplifier, will not instantaneously reach the output. It will take some time, isn't it? And thereby there is a delay in this signal propagation, right? In the feedback. So in the overall feedback also, that delay is introduced, isn't it? Now because of this delay, the system, as we already saw, if there is a delay in the system, then the system can become unstable, isn't it? The negative feedback system can become unstable. So if the delay becomes so large, that is, if the delay becomes so large, then it can happen that the system becomes unstable. Do you get the idea? So thereby there is a correlation between the number of poles and the instability of the system. Fine. I hope all of you understood this. So if I get some yes, then I will be very happy to move forward.
Sir, can you repeat it once?
Yeah, fine. So if you have a doubt, please interrupt me. If you do not interrupt me, I will keep moving forward. Fine. So I was explaining. So what point did you didn't understand? Where did you not understand the whole idea here?
So generally this is negative feedback, right?
This is negative feedback. Yes.
Correct. So how did we get that equation?
Which equation? This
A by
no 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 this sorry. Here I have not written anything fancy here. Oof. What I have done is I simply assumed that the gain amplifier gain, basically this is an amplifier here. Okay, this is not a simple constant gain. Its gain varies with time. Sorry, varies with frequency. And how will you incorporate that in the equation form? It will be A over S plus omega p, right? If there is a pole in the system's gain, it means that, I mean, amplifier gain, then it means that the gain is dependent on frequency, right?
yes, yes, got it.
Yeah. And what I am trying to explain here is that the same pole, this pole here, it behaves as a delay in the overall system, right? We just saw that here. If there is a pole in the system, the overall response is delayed, correct? So that is what I was trying to explain, that in the presence of a pole, anywhere in the loop, okay, here I took a special case of pole being in the amplifier, but it can also be in the negative in the sensing circuit. Okay, this is a this here is a sensing circuit which senses the output and feeds it back to the input. So a pole can also exist in the sensing circuit. So if that happens,
Sir,
it doesn't matter. Yeah.
sir, a pole basically brings a delay in at the
Ha.
output. We can understand this from like if you take the modulus of the transfer function containing a pole, then it
Ha.
will the presence of a pole will basically decrease the result magnitude of that uh, what we take the modulus, right? That way we can
It
understand it.
it will decrease the magnitude after a certain frequency. Yes.
Okay.
Yes. So when it doesn't matter how you want to understand it. I just gave a very simple picture here. I just took the example of the circuit which you are very much familiar with. Okay, circuit which you all know. I mean since standard 12. So this is what I have explained here. Nothing else.
Okay.
Yeah. So in the presence of poles in the negative feedback system, there is a possibility that the system becomes unstable because poles manifest themselves as delay in the system. Okay. Now it turns out that till two poles, I mean with two poles, if the system has one pole or no pole or two pole, the system will always be stable. Okay. It turns out something like that. That comes out from another thing which is called Nyquist stability criteria. Okay. That if the system has up to two poles, the system will never become unstable. Okay. And if it has higher than two poles, so up till two poles, the system is never going to become unstable. So that is why such kind of a system can be called as what kind of system it can be called if the system never becomes unstable. Yes, someone please.
Unconditionally stable.
Yes. Such a system can be called as unconditionally stable because you do not need any condition on it other than the number of poles. Once you have that system, it will never become unstable. Fine. Now, but what happens if you have larger than two poles? If the transfer function, which is open loop transfer function I am talking about, then the system can become unstable. Okay, and and that is why it is called marginally stable, right? Get the idea? The person who asked me what is the difference between unconditionally and marginally stable. Who asked me that question, by the way? Marginally unconditionally stable thing.
Me, sir.
Yeah, so you get the idea?
Yes, sir.
Yes, good. So now, what do I? One second. Yeah. Yes. So I talked a few moments ago. I talked about. I just mentioned this Nyquist stability criteria, right? So what is that? Can someone please bother to explain me? Since you didn't ask a question about that, I hope you understood it. Yeah. Someone, could you care to explain this marginally? Sorry, Nyquist stability criterion.
So that which you told few moments before, that one,
Huh?
sir,
What?
मतलब
Yeah.
sometime before you told about the Nyquist stability criteria, that if a system, negative feedback system's transfer function has less than two poles, about you told that that comes from the Nyquist stability criteria. That one, right?
Okay. Yeah. One second. One second. Sanket, you have a doubt in marginally stable and conditionally stable. Do you? Okay, Sanket. So, if the system, if the negative feedback system, like just explain that if the system is unstable, if the system is stable, irrespective of, I mean, if the system is stable without any conditions on it, on what? On the gain of the system. Okay, this particular constant a into beta. If this constant a into beta, if this can be everything, this can be anything. If there is no condition on this particular in this particular on this particular parameter a into beta, then you can say that the system is unconditionally stable. Okay, but the actual definition is that uh, if the system is stable without any condition, in that case the system is unconditionally stable. So it turns out that if the system, if this negative loop, uh, if this open loop transfer function, which is in this case what, a into beta divided by s plus omega p, right? So if the system has if the negative feedback open loop transfer function has less than or equal to two poles, okay, then the system will always be unconditionally stable. Okay, it will always be stable. It doesn't matter what value of a or beta you put, it will always be stable. Okay, But if the system, if this open loop transfer function has more than two poles, which is if it has equal to or greater than three poles, then you have to be careful of what value of a into beta you choose. Because if you make it very large, then it might happen that the system becomes unstable. You get the point, Sanket? Yes, good. And now Atharv, I interrupted you in the middle. Sorry for that. Yeah, you were saying something about Nyquist stability criterion.
Yes, sir. I think it is not taught till now, sir.
Oh, it is not taught till now.
No, no, sir, because yesterday also with Hanil sir we discussed that.
Uh,
So he told they might teach you afterwards in the lecture videos.
it has already been taught, right? Nyquist stability criterion has already been taught, which is basically the encirclement of 1 comma 0 minus 1 comma 0 point, right? Something like this, isn't
Yes,
it?
sir. Yes, and Nyquist plot is being taught.
Yeah.
Yes,
So what is Nyquist? Oh, Nyquist plot is taught. Nyquist stability criteria is not mentioned, right? That is what you're saying.
yes,
Okay. So okay. So first let me tell. Let us discuss Nyquist plot. So what is Nyquist plot? Yeah. What is Nyquist plot? Please, someone. What is Nyquist plot? Come on, guys. What happened? You just a moment ago you said that it has been taught. So what is Nyquist plot?
Uh, I'm not sure, sir, but I can tell in words.
Yeah, yeah. Please tell in
At
words. No
o-
problem.
yes, at omega 180 degrees, right? If the point lies, that minus 1 comma 0 lies to the left side
Hmm.
in left side of the plane. This
Okay.
signifies that the gain is greater than 1, which is unstable.
Okay. So other guy, any other person would care to explain? Yeah, some of you have been awfully quiet today, so would you care to venture? All right, fine. So Nyquist plot is not what you just explained right now, Maradani Tejasvi. This is the what you explained was not even correct. Was not even totally correct. But you were trying to explain Nyquist stability criterion. Okay, what is Nyquist plot? Is like Bode plot. Okay, it's a plot. It's a kind of plotting mechanism. That's all. Like Bode plot, you understand. You know what is Bode plot, right? Similarly, there is a Nyquist plot, which is a plotting type or technique to visualize the transfer function. That's all. So what do we do in Nyquist plot is in Bode plot, what were we doing? We were representing magnitude as well and phase on different uh, planes, right? So in Bode plot, what was happening? We had a mod of h of j omega, right, versus f, and then we also had a angle of h of j omega versus f, right, that we had something of this kind and this kind, right,
Yes, sir.
correct. But here in this case Nyquist plot, what do? We plot on a Nyquist plot is not for h not for j omega, okay, it is for s plane, okay. Here we do not this thing. Here we take complex frequency as the argument. Okay. So here you remember that in this case, if the transfer function is h of s, we replaced s with j omega, right? And then we plotted Bode plot. Correct? But
Yes, sir.
in this case, Nyquist plot, we keep h of s as h of s itself. And s we know that it's a complex frequency, right? So s has sigma plus j omega, isn't it? This is what is S. There is a real as well as an imaginary part. So what we do, we take sigma here, this is sigma, this is j omega, okay, and then we start making the complex plot. So you know what is a complex plot, right? You have learned in standard 12 complex plots, isn't it? If you want to represent maybe let's say mm, y is equal to f of x, where x can be in general complex, or maybe f of z, where z is a complex number, and in general y can also be a complex number. How do you do it? For every z you start finding a y, right? And you start putting those numbers here. You start putting those numbers here, and eventually when you draw the whole contour, you will get a nice good looking plot, isn't it? So that is what is this Nyquist plot. It's simply a complex plot with respect to S. Okay. So let's say if your h of s is, let's draw one. Let's say your h of s is equal to 1 by mm, s plus 10. How will the plot look like? 1 by s plus 10, how will the plot look like? You start at certain point. So generally I start with s is equal to infinity. Okay. Okay. Are you guys with me?
Transfer function will be at 0.
Yeah, so s is equal to infinity doesn't make any sense. So we start doing it in this way. See, s is equal to what? Sigma plus j omega, right?
Yes.
Right. So what do we do? Okay, that would be confusing to you. Scratch everything that I just said. I mean, this point, please don't care about it. Uh, I'll try a different approach. Otherwise, you'll be confused here. What should I do? Okay. Um, okay, give me a moment. Okay. Yeah. See how you draw an Nyquist plot is See, Nyquist plot is only used to define on the stability, okay? I mean, comment on the stability. So it is only used in particular context. So now let's see a particular example. Here, like I said, h is equal to 1 by s plus 10. Let's say this is h of s is your loop gain transfer function, okay? Which is not s 1 plus 1 by s plus 10, but it is yeah, it is fine. Let's say this is your loop gain, okay? L of s. So what Nyquist criteria says is that when you try to plot this particular when you try to make a Nyquist plot of this L of s, okay, and when you see oh, how will I explain? Mm, okay, ignore this. Okay, now I think I can explain. See, Nyquist plotting is understood, right? Nyquist, what is Nyquist plot? You understood? This is basically plotting with respect to S. Okay, plotting your whatever function you are given, that complex plot you have to make with respect to S, the varying values of S. Okay, when you start putting S values, okay, S basically is sigma and j omega. Then what you will do? You will get certain points here, right? Very complex, we can get a complex point. That complex plot will be the Nyquist plot. That is understood. Now how do you use this plot to define, to comment on the stability is like this. So let's say your L of s is something of this kind, the loop open loop transfer function is of this kind. So what Nyquist criteria says is that you take the Nyquist you plot this L of s, okay, you plot this L of s on the Nyquist on using the Nyquist plotting mechanism, and if that plot, yeah, by the way, you have to plot this L of s for all the right this for all the right for all the points for the argument s here has to be in the RHP. Okay, the sigma has to be positive basically for this case. The sigma has to be positive. When you do that, when you plot this for all the RHP s, then the plot that you get should not encircle -1, 0 point in the anti-clockwise direction. Coming
Sir, your
again,
screen,
yeah,
it's not
yeah.
visible. Not sure whether it's not visible for me.
Others also, are you getting this problem, or is it only for that particular person?
It is visible, sir.
Yeah, Tejasvi, it might be your problem only.
Okay, sir, I will leave. I will leave and I will join in.
Yeah, please. Yeah, so yes, Tejasvi, is it visible now? Good. So I was saying that Nyquist stability criterion says that what you have to do is, first you have to take all the points for if you want to plot any L of s, what you have to do, the s that you choose, that you are going to put here in the L of s, this s has to come from the RHP, okay, right half plane of the S plane, right half of the S plane, okay. When you put all those s here and you start getting values of L means basically the loop gain values, you put it here, okay, and you should and if it happens that after putting that it doesn't encircle -1, 0 point, if the -1, 0 point is not encircled in the plot in the anti-clockwise direction, okay, this anti-clockwise is very important, please note. If it is encircled in the clockwise direction, then you have not nothing to worry. So only when it is encircled in the anti-clockwise direction, which is like this. So if it does something of this kind, okay, then you have a problem. If it doesn't do that, you do not have a problem. So let's say this is one such plot, okay, that it does. So in this case, the system is unstable. The number of encircling here, I mean the encircling here in the anti-clockwise direction, it makes the system unstable. Getting my point? Getting my point? This is the plot of L of S, by the way. Okay, Sanket, what didn't you understand? Okay, you see Nyquist plot is, अच्छा Nyquist plot कैसे करना है? Okay, I'm coming to that. Nyquist plot कैसे करना है? Point is, what is Nyquist plot? You understood, right? It is basically plotting your L of S, or what the negative feedback open loop transfer function L of S. You have to plot with respect to S. That's all. And that plotting, since since S is a complex number, this S is a complex number. That is why what will happen? The overall L of S also, this will be complex, right? So for complex numbers, you need two axes, right? J omega and sigma both. Only then can you represent a complex number, right? So all these points here in this plot, in this green highlighted plot, all these points here are a complex number which represent a certain value of L of S for a certain other different value of S. Okay, so that is what is Nyquist plot. What I am saying is, when you take all the points in the right half plane, okay, right half plane of S, when you for all these points, if you see that there is no encirclements, if there is no encirclement of the, counterclockwise encirclement of the minus 1 comma 0 point, then you can clearly say that the system is stable. How do you plot it? Now I am coming to that. So what it is very difficult to take all the points on this plane, right? So there are infinite points. Actually, it is not difficult; it is impossible, because there is infinite point in a plane, isn't it? Do you agree with me, people? It is not possible to take all the points in a plane, isn't it? Let me, yeah. So people who are there, please say something. Is it possible for you to take all the points in this plane? I mean, there are infinite points. Can you take all the points and make a plot? You will not be able to make a plot. Okay, you will get a lot of different family of plots here. Okay, you will get a family of plots, like one plot is this, okay, the other plot may be this, and so on. So it is very difficult to do all of that. So what he said was, Nyquist said that uh, doesn't matter, you don't need to do all of that. You just need to take an encirclement of the right half plane, the whole right half plane. Basically, instead of taking all the points here, okay, in the right half, you just need to make a boundary which covers all these points. So how is that boundary going to look? Something of this kind. Okay, so what he said was, you do not need to take all the points, just take these points here. First on the j omega axis, like this, okay, from minus infinity to plus infinity in the j omega, and then from in the infinity part only, which is far away something here, in that infinity only, you circle here like this, and then coming back again from minus infinity to like this. So it will basically cover the whole right half plane, right? Isn't it? It will bound the whole right half plane, isn't it, of S. So you have to put only those values of S which is shown by this highlighted green highlight. Okay, so the S, instead of putting all the points inside of this, you just need to take S which is lying on this boundary, on the boundary of the right half plane. Okay, when you take all those S, you will get only one plot here. You will get only one plot here, the plot that is going to resemble something of this kind. Okay, you will get only this plot. And this plot, if it doesn't encircle minus 1 comma 0 in the counterclockwise direction, then you are safe. You can say that the overall system is stable. Getting my point? Good. And how is that? Now, did you understand how to make Nyquist plot and how to check whether the system is stable or not? You will start with this point, okay, 0 comma 0. You start moving up. You means in this case you only vary j omega, okay. So sigma is equal to 0, okay. When you move in this line, sigma is equal to 0, isn't it? This is only j omega which is moving. You move, and then once you reach j omega is equal to infinity, which is very far away, then you keep then you start varying s. Well, sorry, then you start varying sigma, okay. It will be but sigma, when you vary at j is equal to omega is equal to infinity, it will still be infinity only, okay, something of this kind. So let's do an example here. Let's try to make a plot of s is equal to, yeah, this one. L of s is equal to 1 plus s 1 by s plus 10. How will this look? You start at 0 comma 0, right? S is equal to 0 comma 0. So what will be the value for so s is equal to 0 comma 0, right? What will be the value of L of s? Yeah, guys, what will be the value? Come on, what will be the value of L of s?
0.1.
Yeah, so 1 over 10, right? 0.1. So it will be somewhere like this, right? It is a real value, right? It is a purely real value, so it will be something at this point, right? 1 over 10. Good. Now let's say I am increasing the value of j omega, right? I am moving on this line. I am going in the up, right? I am moving up. By the way, I didn't mention this, but the sense of this boundary, how is this? I am moving in this direction, right? Like this. So what kind of a direction is this? Clockwise or counterclockwise? Yes, this is clockwise. So it is clockwise direction, right? And what I said about the stability thing, that has to be anti-clockwise, right? If it is anti-clockwise encirclement of minus 1 comma 0, then the system is unstable. Okay. If it is clockwise encirclement, then the system is stable. So we'll look at it. Don't worry about it. But this point you should remember. Only when it is counterclockwise, then only the system is unstable. Fine. So now if we increase j omega, let's say L of s is s is equal to 0 comma what? Let's say 5j. What is L of s going to be? Come on. What is L of s? 1 over 10 plus 5j, right? Oh, 5j is not a good number. Let's take another number, which is 10j. So it will be what? 10j, right? Correct? Good. So if it is 10 plus 10j, what is, where will it lie on this plane? On this plane, where will this number 1 over 10 plus 10j lie? Where should it lie? First tell me which quadrant. This one, this one, this one, or this one. So this is first quadrant, right? Second, this is third, this is fourth. So in which
The
quadrant should it lie?
first.
It should lie in the first quadrant. And how is that?
It's sigma plus omega j, right?
No. I have sigma plus j omega. This one, na? L of s, when you convert into sigma plus j omega, how will this look? Okay, let's do that. So how do you do it? First take 1 over 10 common, it becomes 1 by 1 plus j. Then you do 1 over 10 divided by 1 minus j divided by 1 plus j into 1 minus j. What will this become? 1 over 10 into 2, right? And on the top it will be 1 minus j. Isn't it? Is this correct or not? Oh, sorry, this will be 4, right? Uh, this is 1 plus 1, 1 minus, no, this is 2 only, right? This is correct. Yeah. So where should it lie? Tell me. In which quadrant now it should lie? How do you decide that? How do you decide which quadrant it should lie? How do you decide that? Looking at the complex number? Tell me. Acha, okay. So this can be written in other words like this, right? 1 over 20 minus j over 20, right? Now tell me which quadrant it should lie. This number. Come on, guys. Okay, in terms of coordinates, what will be the coordinate representation? Cartesian coordinate representation. This is 1 over 20, comma, minus j over 20, right? Isn't it? Yeah, so now tell me which quadrant it should lie. Someone please tell me which quadrant it should lie. This point, where will you find it?
So the y-axis is j, right? So
Yeah,
could you
well,
please
yes,
scroll
yes.
up?
Oh, sorry. This is not Cartesian coordinate. This is minus 1 over 20. Yes, this is the Cartesian coordinate representation. Yes, so yes, the j is minus 1. J is the y-axis. Yes. Where should it lie? Tell me. Come on. Where should it lie?
Fourth.
Yes, it should lie in the fourth quadrant. Yes, it should not take this long. Okay, this is already this is class 12th stuff. Anyway, so this is the fourth quadrant, and its magnitude is definitely less than this guy, right? The earlier point. It is definitely less than 1 over 10. Correct? You see, this is definitely less than 1 over 10, isn't it? Correct. So this should lie somewhere at this point, right? The point should be somewhere like this at this point. Okay. Okay, good. Now, so this is basically your uh, 1 by 20 comma minus 1 over 20. This is done. Now, if you increase the value of j omega further somewhere here, let's say संकेत हमने 1 by 10 plus 10j क्यों किया? Oh, I just took an example here. Okay, I took an example of I'm moving on this line, right? I'm moving on s is equal to j omega line. So I have to मैं इस लाइन पे मूव कर रहा हूँ, राइट? तो इसीलिए मेरे को सिग्मा को चेंज नहीं करना है, सिग्मा 0 ही होगा, लेकिन जे ओमेगा जो है वो चेंज होगा, बस वो बढ़ता जाएगा. तो जे ओमेगा को मैंने एक रैंडम नंबर ले लिया, आप कुछ भी ले सकते हैं, मतलब मेरे को प्लॉट ही तो बनाना है ना. तो प्लॉट बनाने के लिए सारे बीच के पॉइंट्स क्यों ही लूं मैं, छोटे बड़े बड़े पॉइंट्स ले रहा हूं ताकि मेरे को ट्रेंड पता चल सके। तो मैंने 10 ले लिया, 10J ले लिया, राइट? ओके, this is done. Now let's say I take another point which is what? Let's say J is equal to infinity. I mean J omega is equal to infinity. So if you take S is equal to 0 comma J infinity, how will this look? What will L of S? L of S will be 1 over 10 plus J times infinity, right? Correct? So tell me what will be the magnitude of this and what will be the phase of this? Where will this lie, this point? Ganesh, I will come to that. I think you are right. I mean, you are actually right. But let's see. Let's reach that point together. Yeah, I took S is equal to 0 comma J infinity. Basically, I took the farthest point. So how will this? Oh, sorry. I was I not audible?
You are audible.
Yeah, fine. I thought suddenly my microphone was turned off. Okay, fine. I took 2 points now. I am taking the last point, which is S is equal to J infinity, 0 comma J infinity. So tell me what will be the value of L of S here? I mean, where will the point lie for this? Okay, for you to visualize it properly. Yeah, where will the point lie? Okay, tell me what will be the magnitude of this L of S? What will be the magnitude? What will be the magnitude? It should be the magnitude of this one, right? 1 over 10 plus J infinity, right? Isn't it? What is the magnitude of 10 plus J infinity? Come on, people. What is the magnitude of 10 plus J infinity? It is infinity, right? This has to be infinity. Yeah, and then when you take it in the denominator, the magnitude becomes equal to 0. Correct? So the magnitude is 0, and what will be the angle of this? The angle is minus 90. Okay, if you do not understand this, you please work it out. I mean, this has to be understood by you, because since this was covered, this is high school stuff. I am not going to detail of this, but this should be known to you. All right, so this is minus 90 degree. Why isn't it 90 degree? Please argue that and convince yourself why it is not 90 degree. Why is it only 90 degrees, minus 90 degrees? So the overall plot will look something like this. So this will come here like this. It will reach this point, okay? And then after this, after reaching this point, we have covered the first. Basically, we have done this contour like this, okay? And then we start moving in the infinity only, in the infinity space only, okay? When you move in the infinity space only, you are not going to do anything to this point, right? The magnitude will always remain 0. What will change will be the phase. So you are moving in the infinity like this. Then after a certain point, you come to the negative half plane and sorry, negative j omega axis, and you come to minus infinity of j omega, right? When you do that, then you will realize that you are again in this 90 degree plot, sorry, in the origin only, but now the phase will be plus 90 degrees, okay? Phase will be plus 90 degrees. And when you, now when you move in this direction here, you will understand, you will see, try to work it out, okay? You will see that you are moving in exactly this way. So generally it is shown by a dot like this. Okay, so this will be the plot. This will be the Nyquist plot. This is called a Nyquist plot. So this was the direction which we were moving in. Okay, so in this case you can clearly see there is no encirclement, isn't it, of minus 1 comma 0 point. This point is not even encircled here. Okay, so clearly here the circuit is stable. I hope you understood this. The plotting that I just did, go back and try to do it yourself. I mean, I don't have much time to discuss it in detail. I have actually covered it in detail only. The second half, you should plot yourself and try to convince
So
yourself that this is, yeah.
here, right, now we are moving in clockwise direction, so it touches the point. That's why it is stable. Am I correct?
Moving in the clockwise direction, but it doesn't even touch this minus 1 comma 0 point, right? It
Yes,
doesn't.
it.
It is much far away. You can also have a plot like this. You in some cases when LFS is a different. I mean, here I took LFS in this manner, but if you have a different kind of LFS, that it can also happen that this moves like this. It does this, and then it moves something like this. It can happen like this also. If that happens, then you can be. Yeah, in this case also it is not unstable. Okay, let's say you have a LFS of this kind. Now what LFS did we have? This is minus 1 comma 0 point. We had this LFS, right? Okay, this is the LFS that we had. But you can also have an LFS which is like this. I mean, if the LFS is different, then you can have the Nyquist plot which is like this. Oh, sorry. Something of this kind. You can also have this. Okay. But here you see that the encirclement is not anti-clockwise, it is clockwise, isn't it? So this is also not this is also stable. But there can be a third case where you can have a plot like this. If a different LFS is there, you can have a plot like this, which is it goes here, then it does this, and it does. Oh, sorry. It goes like this. Take this example. You can also have this kind of a plot. Okay. Here you have a. This is the encirclement. Okay. See that in this case, you have a anti-clockwise encirclement, isn't it? You see, this is an anti-clockwise encirclement. Understood? You
So
understand?
is it stable? This one anti-clockwise,
This will be unstable.
unstable.
Yeah. So the red one is unstable. Green is. Where's the green? Green is stable even with encirclement because the encirclement was clockwise, right? Then you have the black one, which is stable because no encirclement. Got my point? Yeah. This is unstable because uh, anti-clockwise encirclement. Fine. So this is how you check stability with Nyquist plot. Okay. Fine. Let's now look at some of the examples which I had in mind. And now rest of the things I think is instructor explained clearly. Okay, you can now you can again go back to the week 4's videos and watch it again. You may be able to get some new insights. Okay, you might be able to understand. You should be able to understand why he was saying that with two poles the system can never be unstable. With one pole the system can never be unstable. You can clearly you see this is an example. The first one, this L of S here, this L of S is an example of a system with only one pole, right? There is only one pole in this negative feedback open loop transfer function, correct? So in this case, you can see that it can never encircle whatever value of L of S you choose. If you even if you change this one to let's say 10 to the power 4, it doesn't matter, right? It will always be the same way only. It will never encircle minus 1 comma 0 point, correct? So that is why it will always be stable. Similarly, if you take a two pole system and you try to plot it, you will see that it will also never encircle minus 1 comma 0 point. The worst that it will do is it may touch like this and it will come back, but it will never encircle. Okay, but with a three pole system, encirclement can indeed happen. You try to convince yourself with that. Okay, you can maybe go back and watch the lectures of the instructor in week 4 and come back if you have any doubt. Let's now quickly do some questions and then we'll be done for the day. Yeah, these are some very easy questions. Tell me for the first question. The system has a 40 dB gain without feedback. If the negative feedback factor is 1 over 20, calculate the closed loop gain of the system with the addition of the negative feedback. Yes. So it is said that A is equal to 40 dB. By the way, have you done these questions already? These questions? Means did Henel discuss this with you? Those who have joined Henel's session in the last week, did Henel discuss these with you? These questions? Response would be very much appreciated. I'm asking whether Henel discussed this with you in the last week's session. This question. Okay, fine. No response means everything is fine. Ah, yeah. So you have the system. So this A is 40 dB. Okay, which is equal to 100, and negative feedback factor is 1 over 20. So what is the closed loop gain of the system with the addition of negative feedback? So what is the gain? It is asking what is V out by V in. Tell me, what is V out by V in?
100 by 6.
So it is A divided by 1 plus
1
A
plus a
beta,
beta.
right? Which is 100 divided by 6, right? This is good. And what will be the value in terms of dB? 100 by 6, what will be in terms of dB? It will be 40 dB minus 20 log 6, right? Did you get how did you understand how did I get this?
Yes.
Yeah, good. So you find it and convince yourself that this is indeed the case. This is fine. Let's move on to the second problem. A negative feedback amplifier is a closed loop gain AF is equal to 50 and an open loop gain A is equal to 103. What is the feedback factor beta if a manufacturing error also? What is the feedback factor beta? First tell me this. Hmm. So your feedback of closed loop gain is 50 and your open loop gain is what? 103. So as we just saw, what is closed loop gain? A divided by 1 plus A beta, right? So yeah, so what is beta from here? This 50 is equal to 103 divided by 1 plus 103 beta, isn't it? So here can we ignore 1 or should we ignore 1? What do you think?
So should not ignore 1.
Yeah, good call. We should not ignore 1 because 1 can be ignored only in the condition where 103 into beta
It
is
is
much
not
greater
too
than
high,
1.
sir.
Yeah, but in this case we can clearly see that to get this value 50 from 103, the division factor here cannot be greater than 2. I mean, it should be, it will only be slightly greater than 2. So 103 into beta will never be much larger than 1. So we should not ignore it. So what will we get? So 1 plus 103 into beta is equal to 103 by 50. So quickly tell me what will this be? Right? Good. Now if a manufacturing error results in a reduction of A to 102, okay, what will be the new closed loop gain? Tell me. If this A varies by slightly, if this A varies slightly, what will be the effect? What will be the overall closed loop gain in that case? Come on, let's do that. So A closed loop new would be what? It will be 102 divided by 1 plus 102 into 53 by 103 into 50. So yeah, it will not change much. Correct. So you try to what as a homework, what you can do is you can take it back and see what is the percentage of change in closed loop gain, A closed loop, how much it changes from 50 versus what was the percentage of change in 103 to 102. Basically the you have to check whether, I mean, you have to check how much is the percentage change in open loop gain versus how much is the percentage change in closed loop gain. That is what you should check. Okay, do it as an exercise. Yeah, for the circuit shown below, find exact values of R2 by R1, V0 and Vf. Given that A is equal to 150 and AF is equal to 3. Yeah, Vi is equal to 2 volt. Yeah, tell me. What is AF? AF is the this thing, gain from VO to Vi. Tell me, what is the, how much will this be? Find the exact value of R2 by R1. Okay, tell me what will be this point? How much? What will be the, if this is Vi, what is this? How will you find out what is the voltage at this point? People say something. What will be the voltage at this point? It will be Vi only, right? Hmm. Now, if it is Vi, and you can see that there is a negative feedback here, right? So it should also be Vi, right? So what is this value? What will be the V out here? This is V out. What is this V out value? So it is Vf, or oh, this is Vf by the way. So Vf has to be equal to Vi. Yes, understood. Now this is the equation that we'll be writing will be, so Vi by R air R1, which is this current here, has to be equal to this current here, has to be equal to V out minus Vi over R2. This gives us, oh sorry, I made a mistake. This equation can be, this statement that this node here is equal to Vi can only be made when A is equal to infinity, right? Remember this? Only in the case of ideal op amps we can say that, but in this case the gain is given, it's not equal to infinity, it is 150 only, so you cannot make this statement. So you have to keep this equal to Vf only. This is Vf, this is Vf, right? So Vf is not equal to Vi, but this equation still holds. Vf by R1, which is this current, okay, has to be equal to this current, which is V0 minus Vf by R2. From here what you will get? R2 by R1 into Vf is equal to V0 minus Vf. So this will become, V0 will be Vf into 1 plus R2 over R1, which is, so Vf is equal to V0 upon 1 plus R2 upon R1. Okay, and what is your V0 again from the definition of this op amp? It is V0 is equal to Vi minus Vf minus Vf into A, right? So from here Vf is equal to V0 by V0 by A minus, or rather it is Vi minus V0 by A. Correct. This is your Vf here. So this is equation 1. Maybe you can write it equation 1, and this is your equation 2. So you can simply just equate Vf in both the equations. So you will get Vf Vi minus V0 upon A has to be equal to V0 upon 1 plus R2 by R1. So from here, what will you get? Vi is equal to V0 1 by A plus 1 over 1 plus R2 by R1. So V0 by Vi is equal to 1 by 1 by A plus 1 by 1 plus R2 by R1, isn't it? If you write it in other terms, this will be, did I make a mistake somewhere? It doesn't look like. Yeah, it doesn't look like. So it will be 1 plus, okay, 1 plus A by 1 plus R2 over R1, and this will be A on the top here. Yes. So this is your overall. Okay, let's simplify it even further so that it is A into plus. Oh, rather than doing this, I should have done this. I should take 1 plus R2 by R1 above. So this will be 1 plus R2 over R1 divided by 1 plus R2 over R1 divided by A. Fine. This is your V0 by Vi. You guys already know this, right? In the presence of a finite gain, your overall, so this was the case. 1 plus R2 by R1 would have been if it had been a ideal op amp, right? In ideal op amp, A is equal to infinity, so this term would go to 0, right? So it will be 1 plus R2 by R1 in that case. But here in the presence of non-ideal gain or finite A, we have this particular this thing, right? You already know this. I just did this to make sure that you understand. Fine. And this we know that it is equal to, so this term 1 plus from here we already know that AF is equal to 3, which is closed loop gain is already given as 3, correct? So AF is equal to 3, which is equal to 1 plus R2 over R1 divided by 1 plus R2 over R1 divided by A. Okay. And what is A? A is equal to 150, correct? So replacing that, what do we get? 1 plus R2 over R1 divided by 1 plus R2 over R1 divided by 150 has to be equal to 3. From here you can find the ratio R2 by R1, right? So that is what was required of you. When you solve this equation, you will get what is the value of R2 by R1. You will also be able to get what is V0 because you are given Vi. Because you are given Vi is equal to 2 volt, you can easily find out what is V0 from this equation. Okay. Once you get R2 by R1, you know what is the, I mean, this is already written that closed loop gain is 3. So if Vi is equal to how much? Where is the value? Vi is equal to 2 volts. If Vi is equal to 2 volts, so what is equal to the, what is the value of V0 if closed loop gain is equal to 3? What is V0 by Vi if closed loop gain is 3? Guys, what is V0 by Vi if it is given that the closed loop gain AF is equal to 3? What is V0 by Vi if AF is equal to 3?
3.
Huh? How much? Ganesh?
3, sir.
Yeah, 3, yes. This was just to check whether you were present or not, all of you. Yeah, so if A is equal to 3, so in that case, if Vi is equal to 2 volts, so V0 is equal to 6 volts, right? No maths there. And Vf you can find out when you have, Vf also you can find out, right? From this equation. You know what is Vi, we know what is V0. Vf we can find easily, right? Yes. Someone raised their hand. Have a doubt?
No, sir. Oh, mistake, sir.
Okay, okay, fine. So this is easy, try to do it. Also try to see what happens if I change A by 5%. Again, do the same exercise as earlier. You change A by 5%, see what is the change, percentage change in AF because of this percentage in 5%. You see whether the the change is reduced or not in the closed loop system. Okay. Oh, same question. You know, you do you guys know what is the phase crossover frequency?
Yes, sir.
What is that? What is that?
Sir, phase crossover frequency is like at omega is equal to 180 degree,
Omega is equal to 180
and
degree?
Sir, uh, it is the
Yeah.
frequency at which the phase becomes minus 180 degree.
Yeah. So, Ganesh, you were saying something. I mean, what you were saying,
yeah, sir,
I
what
understand
you
you were
said, I
thinking
was trying
correctly.
to say that.
Yeah, frequency is not equal to 180 degree. Okay, it's a frequency at which the phase becomes equal to 180 minus 180 degree. Okay, cool. So, yeah, at this is basically the phase crossover frequency. So, tell me what is the phase crossover frequency and what is gain margin, by the way? What is gain margin? What is gain margin? It is the gain or magnitude of the dB. Oh, sorry, magnitude minus of dB gain, okay, of the transfer function at phase crossover frequency. Okay, you guys understand this statement? Do you guys understand this statement? Yeah, if you understand, say yes. If you do not, say no. All right. So, fine. So, what is the phase crossover frequency here? How will you find it out? You have to find out what is the phase here, right? So, the transfer function is 1 over, so your h of s is 1 over s into s plus 1, correct? First you replace h of s with j omega, right? So you get 1 over j omega into j omega plus 1. Now you find out what is the phase of this one. What is this? Minus of tan inverse of omega over 0, right? Due to this one. And then minus of tan inverse of omega divided by 1, right? Correct? Am I correct? Do you understand what I did?
Yes, sir.
Good. So, yes. Moving on. So, this becomes, what is the value of this one? What is this?
90.
Yeah. So, since there is a minus here, so it is minus 90 degree, right? And this is minus tan inverse of omega. Correct? Fine. Now, this has to be equal to how much? Minus 180 degree for phase crossover frequency, right? Isn't it? So, here you get tan inverse of omega, which is phase crossover frequency, has to be equal to how much? Minus 180, or rather 180 minus 90, so it will be 90 degrees. So when will it be 90 degrees here? Tan inverse of something is equal to 90 degrees. So what is the value of that something? You take tan both sides, right? So tan inverse of omega pc is equal to tan of 90 degrees. So tan of tan inverse is simply the argument inside of it, right? And what is tan 90? It's equal to infinity, right? So from here you see that the phase crossover frequency in this case is equal to how much? Infinity, right? Right? All right. And what is the gain margin in this case? First, uh, gain margin is dB gain minus of dB gain on transfer function phase crossover frequency. So what is the gain of the transfer function at this frequency? Omega pc is equal to infinity. What will be the gain here?
0.
0. Yes. So at magnitude of h of j omega at omega is equal to omega pc, which is equal to infinity, has to be equal to, will be equal to 0, right? So what is dB gain in dB? What will it be? Minus infinity, right? Right? It is 20 log of 0. So that will be minus infinity. So the gain margin is what? Gain margin is minus of minus infinity. So this is equal to infinity. Isn't it? Getting my point? Fine. So this is also done. 5. Yeah, tell me this quickly. This was mentioned in the first video of this week. Input resistance Ri of an ideal current amplifier or ideal voltage amplifier R. So if an ideal current amplifier, what is the input
Zero
resistance?
and infinity.
Yes, this is 0 and this is infinity. Good, just a revision thing. Very good. Moving on. I think these questions you do yourself. There is a little bit, I mean, there's a math trick involved here. You try to do this. Okay, the answer should be the answer of omega GC. This is equal to root 10, I guess, root 10 or 1 over root 10, something like that. But there is a root 10 involved here. Try to do this. Okay, 7 I will do in the next session. Okay, 7 is a very important question. 7 and 8 I will do in the next session. But 6 you do yourself and try to see. Oh, by the way, what is gain crossover frequency? What is gain crossover frequency?
Sir, the frequency at which the gain is 1 or let's say 0 decimal.
Yes, correct. Exactly. So that so you know that this is good. And phase margin is what? What is phase margin?
It is phase margin is like it is calculated at gain crossover frequency.
Yes.
That
So phase margin is how much you are away from reaching minus 180 degree, right? That is phase margin. So the phase, it is equal to the minus 180 degree minus the difference, the distance between minus 180 degree and the actual phase that you are at that you have at gain crossover frequency. So let's say you have at gain crossover frequency, let's say your phase was minus 130 degrees. So what is the phase margin? Yes, Ganesh. If your phase is
50,
minus 130, yeah, what? Come again?
50.
50, yes. So it is minus 180 degrees. Sorry, it is minus 130 degrees minus of minus 180 degrees. Okay, this is how you calculate it. The phase margin is equal to uh, angle of whatever h of j omega you have at omega equal to omega gc, okay, minus or plus 180 degrees. Okay, that's your this thing, phase margin. So try to do this with this information, try to do this, solve this question, and 7 and 8 I will be solving in the next session. Okay, and the next session will be on Saturday. It has already been announced, but I am just announcing it once again. Next session is on Saturday. This Saturday 6 to 8, same time. Okay, fine. So let's call it a day then. We'll meet again on Saturday. Thank you for joining.